How you doing?
Fine. Think it's gonna rain?
Sure looks like it.
What's all that stuff?
Oh, just some tests. Went down to the mill last week to help the employment people with some screening. Aren't you here kind of early?
Yeah. I came in to fix up a handout for my class. I want to explain once and for all the theory behind the division and multiplication of fractions.
I was looking at that section of these tests earlier. Dismal.
Pretty bad, huh?
The tests are right. These employees don't understand the basic principles of math.
Which basic principles?
Well, one thing they don't seem to understand is that multiplication and division are inverse operations. If you get somewhere by multiplication, you can get back with division.
I think my students understand that, at least with whole numbers.
It's good. Whole numbers is the place to start. As long as they understand that what's true of whole numbers is also true of fractions.
Now that's good. Wait a second. Multiplication and division are inverse operations. So that's the way I'll start my handout then. Now, do I need to illustrate that some way?
I would just put a number series without signs and have the students put in the signs for the operation according to how you read it.
Now, how's that again?
I put down 5, 3, and 15 on your handout and ask the students to determine what sign goes where when you read it from left to right and then when you read it from right to left.
Okay, I've got that. I'll just use arrows to indicate the direction of computation. You read to the right, they multiply, and to the left, they divide.
That's good. Also might be a good idea to show them what the relationship of the terms used in both operations are. You might put down multiplican with the 5, multiplier with the 3, and product with the 15.
And then I'll put in quotient and divisor and dividend for the division terms.
And eventually, you can do the same thing with fractions. Show that the operations for whole numbers and fractions are the same.
I've got it. I've got it. All right, now what's the next most important concept?
I think the additive quality of multiplication. Most people know that when they multiply with whole numbers, it can be a series of additions. They don't seem to realize that when they do fractions.
Well, how can I show that?
Time for the trusty chalkboard. I would put 0 plus 4 plus 4 plus 4 plus 4 equals 16. Nobody questions that. Now for the fraction multiplication. 0 plus 1/3 plus 1/3 plus 1/3 plus 1/3 equals 4/3.
Now, should we do the inverse here, show that division can be a series of subtractions?
That's a good idea. It would look like this. 16 minus 4 minus 4 minus 4 minus 4 equals 0. And for the fraction sequence, we'd have 4/3 minus 1/3 minus 1/3 minus 1/3 minus 1/3 equals 0. This means that it takes 4 1/3 piles to make 4/3.
Yep, you're right.
Multiplication is also progressive steps on the number line. I don't know how you put that in your handout, but it's an important thing to think about.
Multiplication, show progressive steps on number line. Now, that should be done for division as well, shouldn't it?
Right. All you have to do is reverse the procedure. Progressive steps the opposite direction will give you division.
Well, I'll figure out how to show it.
You know, most people, when they multiply with whole numbers, have an idea what the answer is going to be. But they can't do that with fractions.
Yes, I suppose you're right.
I know I'm right, too, but I think I should do this by example. Should make it a little bit clearer. So we have 12 times 4 equals 48. 12 times 3 equals 36. 12 times 2 equals 24. 12 times 1 equals 12. And 12 times 1/2 equals 6.
Yeah, you're letting people see that the product can be smaller than the multiplicand. But I can see why that's confusing. You know, you get used to thinking in terms of whole numbers, and you always expect the product to be at least as large as the multiplicand.
That's right. And division's even worse. People always expect the quotient to be smaller than the dividend.
Now, could you demonstrate that by reversing that last example?
That would be the best way to do it.
Yes, so then the question becomes, what can I divide 6 by in order to get 12?
Or how many halves do you have in 6? Now, this is where the number line would be helpful.
You know, division of fractions means something else, too.
I know. And the thought processes that they're involved in understanding it are more philosophical than mathematical.
You mean because they are a different way of looking at things?
Right. Let's look at this. 48 things divided by 2 means 48 things rearranged into 2 piles. Okay? 48 things divided by 1 means 48 things rearranged into 1 pile.
Okay.
But watch out. 48 things divided by 1/2 means 48 things rearranged into half piles.
Yeah.
No such thing. Either have a pile or you don't. You can't have half a pile any more than you can dig half a hole or cut half a piece of pie.
Okay, I see the distinction, but what's the implication?
If you leave it like this, it makes the division of fractions almost impossible. They would have no reality because you can make a pile half as big as something else, but you have to compare it to 1 pile.
Well, so what are we doing when we divide fractions?
You're asking yourself this: if I have 48 things, like so, and I cut it in half, how many things do I have in 1 pile, or how many piles do I have of a half?
I see. 1 pile, then when you divide it in half, you have 96 piles with 1/2 in each pile.
That's right. This is where your rule for division of fractions comes in.
You mean the rule invert the divisor and multiply?
Right. Times 2/1. This way it helps us to operate as though they were whole numbers. Since we can't have a fractional pile, we have to do something to allow us to treat it as though they were whole piles. So 48/1 times 2/1 equals 96/1, or 96.
You know, that's a lot for students to think about.
I know, but I found that if students don't have a reason to invert the divisor, they'll forget to do it.
Is it enough of a reason to say that the reason we invert the divisor is so the fraction will behave as a whole number?
For most of them, it would be, but for Todd, he'll probably want more. He'll want to see the math behind it.
Yeah, well, I think what I'm going to say on my worksheet, that the rule for the division of fractions, invert the divisor and multiply, is used to make the fraction behave like a whole number. And then if they want any more explanation, they can come to me and talk about it.
Sounds pretty good to me. As long as they know that multiplication and division are inverse operations, know the terms multiplicand, multiplier, product, dividend, divisor, quotient.
And know their relationship to one another.
Sounds pretty clear to me. If they learn that much, you're in good shape.
Yeah. Well, I guess I'll go get this handout typed up then. Hey, what about a cup of coffee after class tonight?
Hey, sounds great to me.
I might even buy you half a piece of pie.
Hi, Steve Wise here. Let's look again at what was on Frank's handout for class. Remember that multiplication and division are inverse operations. By filling in the proper signs, we saw that the multiplicand times the multiplier will give you the product. The dividend divided by the divisor will give you the quotient. Next, we learned that multiplication is nothing more than a series of additions. 0 plus 4 plus 4 plus 4 plus 4 equals 16. And division, a series of subtractions. 16 minus 4 minus 4 minus 4 minus 4 equals 0. Remember that in multiplication, as the multiplier decreases in size, so does the product, as in the following example. However, in division, as the divisor decreases in size, the quotient gets larger. Above all, remember the rule for division of fractions. Invert the divisor and multiply. It makes the fractions behave like whole numbers. Well, now that we've covered all that, let's get back to class and see what's new.
Hey, Martha, what's new?
I got that new job, Frank.
You did?
Yeah, I wasn't sure about it until yesterday, and I never would have gotten it without this class. Remember that test I had to take?
Yeah.
They said I did great on it, even on the math section.
Wonderful.
So thanks a lot.
Well, you're welcome. Hey, did you all hear Martha got that new job?
Congratulations.
Anybody else got any good news?
Well, as a matter of fact, this farmer found out that a hen and a half could lay an egg and a half in a day and a half.
No, you're not going to get me involved in that crazy thing again.
You know, that is a very old story, Todd. You mean you haven't figured that out yet?
Oh, sure, I've solved it. I just can't get any of these unimaginative people around me to even think about it.
Okay, ask me the question so I can write it down and I'll work on it.
All right. If a hen and a half can lay an egg and a half in a day and a half, how long will it take 6 chickens to lay a dozen eggs?
Got it.
Todd, where do you get a hen and a half?
From an egg and a half.
All right, that's enough of that. All right. Tonight we are going to explore the fascinating world of multiplication and division of fractions. All right, Bill, help me pass these things out. Would you pass them
I'll
back
take some
there?
over
These
here.
worksheets? Okay. What these sheets show is all the math that we're going to be working on tonight and next week. But tonight, all we're going to do is just be solving problems. I'm just going to flat out teach you how to multiply and divide fractions, all right? Straight computation from the word go. But there is one other part to this plan.
Uh-oh, I knew there was a catch to it.
You got it. Next week, it's going to be your responsibility to bring in examples that you have met in real life using multiplication and division of fractions, okay? All right, now first, take a look at the second page of this handout, okay?
Ooh, yay, rules. My favorite things.
All right. Now, rule number 1, you see, is so simple you can probably follow it all by yourself, okay? Rule number 1 says, to multiply fractions, multiply the numerators by the numerators and the denominators by the denominators.
Then just multiply straight across, right?
Well, let's do this example to be sure, okay? What is 3/8 times 5/6? Todd, you finished?
Yeah, I've got 5/16 after I reduced it to its lowest term.
Did you all get that?
Right.
Did you reduce it to its lowest term? Uh-huh. Okay. Let's do another one, all right? What is 3/8 of 1/2? Now, of in fractions means to multiply. Bill?
3/16.
Good? Okay. All right, on to the next rule. Rule 2. To multiply a whole number by a fraction, express the whole number as a fraction.
You mean write the whole number over 1?
Yep, and it just multiplies straight across.
Everyone okay? Okay? All right, here's an example like that. 7 times 3/4. Sue, you got a good answer?
5 1/4.
Everybody get that?
Mm-hmm.
Well, you must be right then. All right, good. Maybe I'll stump you this time. Look at rule number 3 and the example. To multiply a fraction times a mixed number, express the mixed number as a fraction. Okay? Now, what is 2/3 of 5 1/7? Sue, you got an answer you like?
Yep-o, the answer I got was 3 3/7.
Uh-huh. Now, how did you get that?
Well, what I did was change the 5 1/7 into a fraction and multiplied it just like always.
Okay.
What's
Okay.
next?
All right. Rule 4. To multiply a mixed number times a mixed number, express both mixed numbers as fractions and follow rule number 1. Okay? Now, here's an example. 3 5/8 times 2 5/6. Now, this is a little harder now. Bill, you got an answer?
Yeah, I got 10 13/48. This kind is a lot of work.
Yeah, mixed numbers can get out of hand in a hurry.
You know, we didn't have very many examples. I hope I can remember to follow these rules.
Are there any questions before we go on to division?
Nope.
You didn't say anything about cancellation.
You're right. Should we have a rule about that?
Well, if we do that, shouldn't we have another rule that tells us how to take a mixed number and turn it into a fraction?
I'm flexible. What do you think, Todd?
Well, I'm for just keeping the number of rules small. I mean, if we have a number for, or a rule for cancellation, it'll only say cancel when you can, and we already know that.
Well,
So I'm for just keeping it 4 rules.
that's a good point. Everybody agree about that?
Yeah.
Okay. All right, then. Let's go on to division. Now, you'll be pleased to know that there is only one rule for the division of fractions. Anything else you need to do has already been done.
Just one rule. Great.
All right, here it is. Now, you've heard this all before. To divide by a fraction, invert the divisor and follow the rules for multiplication.
And just multiply straight across.
What more can I say? That's the whole story, Todd. But nonetheless, we'll check it out, okay? You knew we'd do that, right? All right, see what you get with this. What is 7 divided by 2/3? Todd, what's your answer?
I got 10 and a half.
Now, that's what I got, too, but I get confused when I divide by fractions. I always think when I divide that the number I end up with should be smaller than the number I divided.
What do you think, 10 and a half's the wrong answer?
No, I think it's the right answer, but it just surprises me.
Well, I said that I wasn't going to explain anything tonight, but let me see if I can just give you something to think about.
Thanks.
Okay. The problem 7 divided by 2/3 equals 10 and 1/2 is like 15 divided by 3 equals 5, right? Okay, now I know that what bothers you is the relative size of these numbers, right?
Right, yeah.
Okay, now look, let's just take the signs out of here, okay? Now I know all of you, when you read this, you would say, left to right, 15 divided by 3 equals 5, okay? And if you said it the other direction, reading to the left, you would say 5 times 3 equals 15, right? Okay, well then shouldn't it be the same with 7 and 2/3 and 10 and 1/2? Here, write down on your paper 10 and 1/2 times 2/3 and see what you get. What do you think, Martha?
Well, I thought it was right. It's just my emotions that get all messed up. I just don't feel like it's the right answer.
Well, maybe you'll feel more like it's the right answer if we do a few more problems, okay?
Okay.
There's only one more part to this division thing anyway. Can anybody guess what it is?
Mixed numbers?
You got it. Mixed numbers. Okay, try this problem, all right? What is 3 1/3 divided by 3/5? What do you get, Bill?
5 and 5 ninths. How do you feel about that, Martha?
Now, you quit picking on me, Bill. That isn't fair, Frank.
Does a mixed number divided by another mixed number work the same way all the time?
Sure, sure. Let's try this one here, okay? Say 2 1/2 divided by 6 1/3. What do you get, Sue?
1538.
1538. What'd you all get? Huh? Is that right? Okay, well, you must be right again then.
Okay.
All right. That just about takes care of all this. We've done all of the examples of all the possibilities, I think. We've also run a little bit over time, so let's get out of here.
I need to get out of here. I gotta catch my ride. You need a ride, Bill?
I could use a ride, too.
Now, listen, remember, you're part of the deal, okay? Next week, I want to see some real-life examples of multiplying and dividing fractions, okay? All right. Don't forget now, study your rules. See you next week.
Here are some rules you need to remember and some examples to help clarify each one. To multiply fractions, multiply numerators times numerators and denominators times denominators. To multiply a whole number by a fraction, express the whole number as a fraction, then follow Rule 1. To multiply a mixed number times a fraction, express the mixed number as a fraction and follow Rule 1. To multiply mixed numbers, express both numbers as fractions and follow Rule 1. To change a mixed number to a fraction, multiply the denominator of the fraction times the whole number and then add the numerator. This gives the new numerator. The denominator stays the same. To divide a fraction, there is one specific rule to follow. To divide by a fraction, invert the divisor and follow the rules for multiplication of fractions. Here's an example of that process.
Okay, folks, are you all ready to take care of your part of the deal on multiplying and dividing fractions? Now, remember now, we said real-life examples about what we were talking about last week, right? Okay, who's going to be first?
Well, I had this situation come up.
Okay, Bill, come on up here to the board and show us.
Okay. These guys brought this metal bar into the shop and said they wanted it cut into pieces 10 inches long, and he wanted 20 pieces. Now, I knew that 10 inches is 5/6 of a foot. Now, the bar was 16 feet long. So, to find out how many pieces I could get out of it, I divided 16 by 5/6. Let's make this a fraction. And we want to invert the divisor. There we go. That would be equal to 96 over 5, or 19 1/5. So, it turns out we can't get 20 pieces out of the 16 pieces. So I tell these guys it can't be done. And they say, well, give them 19 pieces then. Now, the math says you'd get 19 1/5 pieces, 5/6 of a foot, or 10 inches long. But you don't. See, every time you cut the bar, you lose about 1/8 of an inch. You lose it in the shaving, see? So, I told these guys that, well, if you cut it, let me see. Now, if you cut it 19 times and you lose 1/8 of an inch each time, you make that a fraction. You'd lose a total of 19 over 8 inches, or 2 3/8 inches. So, I told these guys you can't, not only can't you get 20 pieces, you can't even get 19 pieces. Now, along about this time, they started acting a little bit unfriendly and shifted that bar around into sort of what I took to be a threatening position. So I said, look, let me explain this to you. So I pulled out my notebook and said, if you want to get 20 pieces 10 inches long, you would have to multiply 20 times the 5/6 of a foot. We'll make that a fraction, so it'll be 100 over 6, which is equal to 16 2/3 feet, which is the same as 16 feet 8 inches, plus the 2 3/8 inches that we lost in the shavings, or a total of 16 feet 10 3/8 inches.
All right, Bill, that's an excellent example of making math work for you. Super.
Yeah, I think it saved my skin.
Super. All right, who else has got a use for fractions?
Let me tell you what happened to me.
Okay.
We had this going away party for a friend of mine, and I was supposed to go out and get the party favors. So I went out and I found these real cute little place cards that cost 58 cents each. Now, my budget was $7, but I didn't know how many place cards I could buy for that much money. So I divided 58 cents into $7, and guess what? I could buy 12 place cards, and there were exactly 12 guests at the party. Neat, huh?
Well, why don't you come up here to the chalkboard and show us that calculation?
Oh, I used a calculator.
You what?
I used well, I had it in my purse, and I just didn't think that it would be wrong to use it.
Martha, do you know what we think about people who cheat on math problems?
Martha, what did you do about the tax?
Oh, I just paid that by myself.
You know, in both of the examples that we've used so far in real-world situations, things don't come out in nice, neat little packages like they do in our math books, do they? It means you're going to have to do some thinking for yourself, like Bill did when he decided to include the shavings in his computation. Now, the math books would not have even mentioned shavings, and they would have said that you could get 19 pieces out of that bar, right? And Martha, I don't know what to say to you. I'm absolutely certain that the math books would not have suggested that you use a calculator. All right, we haven't heard from you yet, Todd. What have you brought us?
Well, last Wednesday night I was at home watching the Late Show. Oh, must have been about midnight when the phone rang. Well, I answered it, and the operator asked if I'd accept a long-distance collect call from Alaska. Well, I said I would. She put the call through. Then this voice on the other end of the line said, if a hen and a half can lay an egg and a half in a day and a half. Was that good? Was that great?
Todd, that is the sneakiest trick I've ever heard. It's creative, but it's sneaky. All right, what did you tell your mysterious caller?
Well, did you know this is a trick question?
No kidding. Come on, Todd.
Well, it's the time that messes you up. Once I'd studied it a while, I began to grasp what was going on. One hen can lay one egg, not in a day in 1 day, but in a day and a half. Well, once I figured that out, it was easy to figure out how long it'd take one hen to lay a dozen eggs. That's 12 times 1 1/2 days. Hen number 1, there's 18. One hen could lay a dozen eggs in 18 days. So 6 hens, working together, of course, could do the job in 1/6 the time. That's 1/6 of 18, which is 3. 6 hens can lay a dozen eggs in 3 days. There it is.
Well, you are absolutely right. No doubt about it. Good, good. Now, when did you discover that the time element wasn't what it appeared to be?
Well, it was kind of hard for me to think of a hen and a half. So I thought of 3 hens. 3 hens, twice as many, could do the job in, well, half the time. So once I'd figured that out, it was easy to calculate how long it would take. I guess I used the logic before I used the math. But at least I used logic. I didn't use a calculator.
No. You know, as crazy as this egg problem is, it does demonstrate a basic principle of division of fractions. Now, Todd was able to understand, or to begin to understand, the relationship of the numbers once he had started making things behave as though they were whole numbers. Now, that's why we invert the divisor. So the relationships will be like they would be if they were whole numbers, okay? Good session. Okay, well, that's it for tonight. I don't want Todd to be late for his phone calls tonight.
Well, that's it for this session. I'm Steve Wise. See you next time.
Local funding for GED on TV has been provided through a grant from the employees of DLH Industries, manufacturing